This is the video lecture for our notes on section 6.3.3, which is about elastic collisions. And this is a chapter about momentum, so let's just go back and remember a couple of things about momentum. And the first of which is momentum is conserved in a collision if the collision between the objects happens in an isolated environment. In other words, there's no external forces acting on the object. So, um, in that situation, regardless of the type of collision, um, momentum is conserved, and that is the sum of the momentum of all the objects in the system before the collision is equal to the sum of the momentum of all the objects after the collision. And we can differentiate further between the types of collisions, and we've done some work on inelastic collisions. And a perfectly inelastic collision is when two objects collide and they stick together and they move as one object. And in a perfectly elastic collision, that doesn't happen at all. In fact, and that's really the subject of what we're dealing with here. In an elastic collision, the two objects collide and momentum is conserved, but also kinetic energy is conserved. So the sum of the kinetic energy of the objects before the collision is equal to the sum of the kinetic energies of the objects after the collision. And this is a pretty reasonable approximation. Even though no collision is perfectly elastic, we can make some assumptions when the loss of kinetic energy is negligible. And this is kind of like when we ignore friction or air resistance in a calculation. And like I said right here at the end, the examples of perfectly elastic collisions are collisions between billiard balls, if you're playing pool, and also the Newton's cradle. And I strongly urge you to check out the video that I linked to in the digital version of this document right here, because it just has a really beautiful collection of examples of how the Newton's cradle conserves momentum and kinetic energy. So let's get on with it here. We have we don't really have any new formulas here. Instead, when we have an elastic collision between two objects, we know that the momentum is conserved, and so I'm going to sum up the initial momentums of these two objects A and B, and I know that that has to equal the sum of the final momentums of those objects. That's one of the reasons why we actually study momentum, is because it's a conserved quantity, and that helps us make predictions with our calculations. We also have the conservation of kinetic energy, and so I will write that as using the same subscripts. Don't forget to square your velocity. So that sum of the kinetic energies of the objects before the collision is equal to the sum of the kinetic energies of the objects after the collision. So we use these two equations, and really a lot of the problems that we're asked to solve in the book is really just a matter of conserving momentum to find a particular velocity, usually the final velocity of one or the other of these objects, and then just verifying that it was an elastic collision by showing that kinetic energy was conserved. But what we can actually do is because we have two equations here, and they both involve the same, let's see, 6 quantities, the masses of the objects, and then the initial and final speeds of the objects, velocities of the objects, I should say. And so what we can really do with this is, now instead of just having to know all 5 out of the 6 of those things, and solving for the last one, we can use both equations together and to solve for two unknowns instead of just one. And that's one of the things that we really get when we assume that a collision is elastic, or when we're allowed to assume that a collision is elastic. And so what you can do is you can actually combine these two equations together using algebra, and it's a pretty many step process, and you can actually solve the two equations for the final velocities of both objects. And the reason why that's interesting is because often you know the initial velocity of two objects as they're moving along, and you know their masses, and we want to predict what's going to happen after the collision. So that's why it's useful and interesting to know, to be able to compute those final velocities. Let me just show you the result of this. The final velocity of object A is actually the mass of object A minus the mass of object B divided by the sum of those masses, and all that times the velocity, the initial velocity of A, and we keep going here. 2 times the mass of B divided by the sum of mass of A plus mass of B times the velocity, the initial velocity of B. So what we're really looking at, this looks complicated, but let me just explain what we're looking at here. The final velocity of object A after this collision is basically a combination of the initial velocities of the two objects involved in the collision, and the proportion of which of these velocities is determined by the masses alone. And that's what these little in parentheses here show us, that these are just the masses, some combination of the masses of the two objects. And we have a very similar equation that we can use to compute the final velocity of object B. It's 2 times the mass of object A over MA plus MB times VAI plus the mass of B minus the mass of A divided by the sum of the masses times the velocity of the initial velocity of object B. So again, these two equations come from solving this system of two equations for the final velocities. And I'm just going to finish up part one of this lecture by filling in these other two these other two pieces of information. So we know, of course, that m is mass in kilograms, and velocity, v, is velocity in meters per second, and that's for our SI system of units. And that's really the only two quantities we're dealing with. But I will make a couple of important notes that I like to repeat over and over again. Velocity is a vector. Okay, so that means you must mind your signs. Okay, some of these velocities might be negative and some might be positive if the objects are moving in different directions, and it's important to consider that in the very first step of solving problems when we list the things that we know. The other thing that we should really remember and continue to do is to use subscripts intentionally. And again, what that means is really when you're listing those things that you know, that information that you're given in a problem, it's important to attach the appropriate subscripts so that you know which object you're talking about. If there's two objects in a problem and you just say m equals 17 kilograms, then we don't know which object actually has a mass of 17 kilograms. So use your subscripts to to make that clear. And also, even the same object might be moving at a different velocity before or after a collision, so we have to use subscripts in order to determine to be really clear about which velocity we're talking about. So in part 2 of the video, we'll explore some of these questions down here in developing understanding.